We'll start off by completing the problems from the previous lesson from Thermodynamics 1 and do problems 11 through 27. So these are solutions continued from lesson 10, Thermodynamics 1, typical exam problems. When we finish these, then we'll go on to do the problems for lesson 11. In problem number 11, we have a 10 cubic meter tank, uninsulated, contains nitrogen at a pressure of 2 MPa and a temperature 250 degrees C. The temperature of the environment surrounding the tank is 35 degrees. I'd like to find what entropy change the surroundings experience after a long period of time. Well, after a long period of time, the temperature and everything will settle down to be 35 degrees, so the final temperature will be 308 K. Now, the change in entropy is given by the ratio of Q over T0, where T0 is the 308, but Q is equal to mc sub V times the difference between T2 and T1. Now, m in turn can be replaced by PV over RT. There's a C sub V again, T2 minus T1 over T0. Going down one line below this now, we can now replace R by Cp minus Cv. And so we have P, V, C sub V, T2 minus T1, Cp minus Cv, T sub 0. Well, this temperature that we're dealing with here is the difference is 215 degrees between the surrounding temperature and the nitrogen. So this T2 minus T1 is 215. V is 10 meters cubed, C sub V is 0.743. We look it up in a table for the specific heat of nitrogen. Down below here we have C sub P minus C sub V, that's the definition of R. There's the temperature converted to K, 250 plus 273, and there's the T0 from over here at 308, and out comes 66,818 joules per degree K. So the answer would be C is the best choice. In problem number 12, we have a Carnot cycle refrigerator that operates between minus 11 degrees C, which is the low temperature, and 22 degrees C, which is the high temperature. What's the coefficient of performance? Well, the coefficient of performance, or the COP, is the ratio of TL over TH minus TL, where these must all be done in terms of degrees K. So the T sub L is equal to 262. And the T sub H will be equal to 295 when we add 273 here. So we end up with 262 divided by 295 minus 262, and this gives me a result of 7.9, which is D is the answer to this problem. Problem number 13 starts off looking like a long problem, but it's really a very short problem. If we look at a diagram, we'll see we have a plot of enthalpy versus entropy. There's the vapor dome, and we can see the cycle shown here for the Rankine steam cycle. The nice thing is that in this problem, at every point along the way here, A, B, C, D, E, and F, we're given on the chart what the enthalpies are. And that's all we need to solve the problem, because the thermal efficiency of a Rankine cycle is given by W out minus W in over Q in, where W out is really the distance between D and E. So W out can be read right off the graph as the difference between the 3061 we have up here and the 2336 we have at E. So it's this distance in here. That's W out. W in is this distance over here. And this distance would be the difference between H sub A and H sub F. So there you have the output. This is W in, W out. And so these numbers can be read right off the graph. And then the Q in is the difference between D and A. This distance between A up to D represents Q in. Is HD minus HA. When you put these enthalpies in and you do the calculation, you come up with 25%, which is choice B for the correct answer for number 13.